And for my ICT 4485 NoSQL databases final project, I'm creating an application called MeBill, which is a centralized portal for people to receive and initiate payment for e-bills, and also for businesses to register and securely deliver e-bills to clients and receive payment for them. The benefit to customers is that they would have a centralized place to receive those e-bills where they do not get lost in their email inbox and they're not tied to a specific bank. And the benefit to businesses is they can save on postage when customers opt in for electronic delivery. This presentation describes my project, how the type of NoSQL database was selected for the solution, the data design, and the queries and pseudocode to run and implement the NoSQL part of the solution. So the first thing I wanted to talk about was deciding between implementing this in a relational database management system versus a NoSQL. When deciding between the two, the choice depends on the business case and the requirements for the accompanying applications. NoSQL databases often have a lower cost of ownership and higher performance for solutions handling massive amounts of data. However, there are many situations where relational database is a better alternative. It's common within an enterprise to see a combination of relational and NoSQL databases used. NoSQL databases are designed to easily and cost-effectively scale in order to maintain performance when handling high volumes of data. Cheaper multiple servers can handle the load and provide high availability, but the scalability often has a trade-off with the consistency of the data. There may be a period of time where dirty reads could be encountered as data is replicated from one server to the others, but NoSQL databases provide eventual consistency. Also, the schemaless nature of NoSQL databases means the data model can be changed easily, often with a large impact to the overall system. And there are trade-offs for both systems. For this application, as I described, it's an electronic billing application where consumers can register to receive electronic bills in their portal, initiate electronic payment of e-bills. And businesses can register to deliver e-bills. They can deliver e-bills and receive electronic payments. That's my project idea. So the characteristics of this application are, there's not really a need for flexible schemas like what would be provided by a NoSQL database. It doesn't vitally need transactional capabilities. It could work just fine with eventual rather than immediate consistency. It doesn't need in-memory caching that some NoSQL databases provide. It doesn't have a lot of relationships in the data model, which would lend it towards the use of a graph database. And it'll eventually have multiple terabytes of data. And really that last point is the reason I would select this as a candidate for a NoSQL database implementation rather than relational database. So in choosing the NoSQL database type, I first considered the graph database. Graph databases are suited for situations where relationships between data elements are very important, where there are many relationships in bulk and where there is a large volume of data and relationships. Graph databases like Neo4j that we studied in class offer capabilities where a high volume of relationships can be queried with low latency. And the MeBill application doesn't really have the characteristic where data would best be represented by relation to other data or traversal of relationships to query the data. So an alternative NoSQL database product selection would probably be better. So next I considered key value databases. Key value databases are simple, flexible, and fast. Data is located using a single key, and there are not a lot of other searching features. Key value databases are commonly used for session information in web applications. Redis, that we looked at in class, is a key value database where data is stored in memory, resulting in tremendous read and write speeds. I feel the MeBill application needs more complexity than easily offered by a key value database. And the eventual volume of data will result in needing an immense amount of RAM to keep it all in memory. An alternative NoSQL database would probably be better. Okay, a document database is what I considered next. A document database is a key value store where documents are assigned and retrieved using a unique key. Everything related to a given database object can be encapsulated in a single document that is written and read all at once. Similar documents are placed in a collection. For example, maybe a bills collection might contain individual bills, and a bill would be a document that would contain the basic information about that bill, the biller, the consumer, the amount, the due date, plus maybe it would contain a sub-document that would include all the line items in that bill. Fields can vary in a key value in a document database from document to document, providing great flexibility. A document is often represented in a JSON structure, such as in the database that we looked at in class, MongoDB. Document databases are highly flexible, highly scalable, and have a good replication capability, auto sharding, real-time analytics, and are good for low latency reads. A document database like MongoDB could certainly work for this solution. Next, I considered a column family database. Column family databases like Cassandra are good for high volumes of writes, large data volume, high availability, scalability over potentially many servers, and high performance at a large scale. Column databases store data by columns. A column family is somewhat analogous to a table, where a column family groups related data which is often accessed together. Column family databases are similar to document databases in terms of pros and cons. As compared to a document database like MongoDB, Cassandra tables contain semi-structured data, which means the table has a number of consistent entries on which queries can be executed. Also, Cassandra features the Cassandra query language, or CQL, which is similar in syntax to SQL. Both the MongoDB and Cassandra solutions have a time-to-live feature, which would be useful for retaining the bills for 3 years and then automatically purging. I've chosen Cassandra as a NoSQL database for the MeBill application. When compared to the Mongo database option, the column family option just makes a little more sense to me. Okay, when modeling a database using Cassandra, the set of tables and their structures are largely determined by the set of queries that will be run by the application accessing the database. And I've listed some types of queries that would be run for this application. I decided to implement the solutions database using 5 tables. 2 tables contain consumer and business entries. Bills are denormalized into 2 tables. Bills by consumer and bills by business by day. Finally, line items by bill is a table that stores individual line items that comprise a complete bill. And now I'm going to go over the queries for key space and table creation. And I have put those in this CQL file, and I'm just going to execute them here, if I can. Okay, so the first command has created the key space, and the second one is an instruction to use that key space. The next thing I did was created a user-defined type called address, where I have the city, street, state, postal, and country in there. And this will be used in both the business and consumer table. Next up, I created the businesses table shown here. The businesses table has a partition key of name and business ID. It includes this unique business ID, the name of the business and address, the routing number, account number for payments, and the time UUID for when it was registered. Moving on, the consumer table looks similar, where it has a unique consumer ID. This would be the user's login ID for the web application, their name, address, routing number, account number, and when they registered as well. Next up, the primary key is the consumer ID only. Next up is this table, bills by consumer, where the primary key here is the consumer ID, the due date for the bill, and the bill ID, where the bill ID is I'm reusing the time UUID construct as the bill ID. So this information about the bill from the consumer's perspective includes the amount, bill date, due date, description, status, and the paid date. This last statement here in the definition of the table defines the time to live as this 94 million value, which is 3 years. And this shows the math how I got that. Finally, I created a secondary index on the status column. So the status column will be either paid or unpaid. Moving on. There's a similar structure for the bills by consumer, where the business ID and the bill date are used as the partition key, and also a secondary status index is created. Then finally, I have this line items by bill, where the bill ID and line are used to describe the entries within the bill. Populating data is next through these queries. I inserted into the business table these businesses, and here is the output. Next up, populating the consumer. And then finally, the next set of queries are for generating the bills. I'll show you what one looks like, and then I'll run all of them. So I have in a batch statement inserting into the bills by customer table, the bills by business by day table, and then inserts for the line items by bill entries. And that's done. I did it in batch to sort of simulate a transaction, and the outputs of those are here. Now I'm going to run the rest of the queries to insert lines into those three tables, and then I did a select on those three tables, and the outputs shown here. Okay. Next up is individual queries, and I'm going to rifle through this a little bit because I'm running out of time. This one selects a consumer by ID. This one selects the billing city for a consumer by ID. This one selects all the unpaid bills for the customer and the paid bills for a customer. This one, these queries here select past due bills for the customer and the bills for the customer for a month. Next up, this one selects line items for one bill. Then this is a more complex query where I am deleting a line item from a bill and readjusting the total amount. So this starts with 6 line items and an amount of 23.26, and this delete query and then this update command reduce. We're removing this line 4 with $10, so the 23.26 becomes 1326, and the line items no longer have line 4. Finally, these queries select bills by the biller on a certain date in a date range. Let's see, this one's unpaid bills in a date range. And that's the end of my data manipulation. I did the data entry. The data manipulation, I just demonstrated those scenarios. What I learned in this project, I learned that Cassandra, the database model, is very dependent on the queries to be run. Denormalizing that data, like I had the bills in both bill by customer and bill by business tables. The second time around with denormalization is a good thing. The second time around with Cassandra, the partition key concept became more clear to me. And I consider Cassandra pretty weak in the data aggregation capabilities, and a lot has to be done in the client code. Overall, in this class, I felt like I got a great overview and valuable exposure to NoSQL databases, and I feel it'll help me with my career. Thank you very much.